We are going to talk about VSEPR theory and molecular geometries. Again, Lewis structures are the most important thing to be able to discuss. Once you get the Lewis structure down, then you can relate to the table. Now, the structure of the compound determines their properties. And that would be looking at polarity overall. It would be looking at the shape of the molecule, and that's what bonding theory predicts, the shapes of the molecules. Valence shell electron pair repulsion theory, VSEPR theory. It identifies that when we have a central atom and we have some bonding occurring, what we'll call electron groups, we need to give them as much space as possible. We know electrons repel. And so if electrons are getting close together, they're gonna start repelling each other, and that's not good. We don't like repulsions, we like attractions, right? We wanna just keep this attraction going and not the repulsion. So when we have things like two electron groups, what we'll see is that they want to be spaced out as far as possible. Two electron groups would be what we call a linear geometry. Very important example, CO2. Those two electron groups are oxygens, 1, 2, around the central atom. They like to be spread out 180 degrees. Now, our incomplete octet with boron is a very important example of the trigonal planar geometry, the 3 electron groups. Again, the 3 electron groups being 1, 2, 3 outer atoms. Boron will make those outer fluorines equidistant from each other, which is 120 degrees. Now, CH4, our 4 electron group example, looks at carbon in the center and says, yes, if there are 4 hydrogens all around him, we're not going to be planar anymore. We're not going to be flat. What we actually pop into is a tetrahedral geometry. Now think about these 3 on the bottom, these 3 hydrogens being similar to a triangle with 1 flagpole at the top, right? So it's changing into what the tetrahedral comes from is the tetrahedral crystalline structure that we would be mirroring this idea off of. Now, a domain is the same thing as an electron group. I like to think about it as things around the central atom. For 5 and 6 electron domains, we have a much different structure because of the expanded octet idea here. What we start to see is equatorial positions, things around the middle, the equator. Same thing over here on the 6 group, versus the axial positions, our flagpoles here, up and down. These structures you do not have to draw. They would just be being able to look at a Lewis structure and identify how many things around that central atom, and so which shape do we go into. All of these shapes have different bond angles and different names, so be very careful with their names. I'll show you the overall chart in your textbook in just a little bit. Now, lone pairs count as a group. Even though you can't see them, a lone pair is already going to be in a specific position. It takes up space. So when you think about NH3 and H2O, if you were to draw that Lewis structure, you'd see that there are lone pairs. Now there is a slight distortion of the bond angles. We see that these are less than 109.5, the normal 4-domain system for the tetrahedral, but they still have that tetrahedral geometry. What we think about instead of these is giving them a couple of specific names to identify that the electron groups, some of them are bonding and some of them are non-bonding. Same thing for the trigonal bipyramidal electron geometry, we don't put that lone pair in an axial position because of the pair bonding repulsions. We would put it in an equatorial position only. And again, even though they might look like, oh, they're invisible, they're just there on the sulfur, they actually do take up shape. So make sure you imagine that shape counts the lone pair. We'll practice with VSEPR theory a lot together in class. That will also be our way of practicing with Lewis structures. You can have 2 lone pairs in that 5 electron geometry count. You can have 6 lone electrons or 3 lone pairs. This again is a good example of, yep, that's a noble gas. We can get it to react. Don't be so surprised. We'll go through all of these VSEPR theory molecules in class together. The 6 electron geometry system could have 1 lone pair or 2. You can place that 1 lone pair anywhere, axial or equatorial. It doesn't matter because of the 90-degree bond angles all around. However, when you put the second one on there, they have to be on opposite sides in order to reduce the electron repulsion. Here is the overall chart that's really important for us to be able to look at. When you're looking at this chart, you start reading over on the left-hand side and identify just how many things total around that central atom. Then you would want to say how many are bonding versus how many are alone pairs, and then determine the electron geometry and the molecular geometry. We will focus on the molecular. These are the specific names based off of how many bonding versus lone pairs, non-bonding electron groups we have. These are very important to know. Approximate bond angles are very important. Again, you'll see instead of the 107 and the 104.5, we'll just say less than 109.5 when you start getting lone pairs. That's a-okay with me. I don't need the specific number for the molecular geometry, but the general number you see here in this column is going to be important for us. Again, you do not need to know how to draw. Know only the molecular geometries and the bond angle. Those would be the most important. You do not need to learn how to draw these in 3-dimensional shapes. The Lewis structure will suffice. These guys are a-okay for us to keep. So don't worry about doing any of this 3-dimensional colored format of the ball and stick models. So overall, to use this chart to be able to predict the structure and the shape, you would need to draw the Lewis structure, count up the number of things around the central atom, classify each one of those things as bonds or lone pairs, and then refer to the table. Remember, multiple bonds just count as one group. What we saw in carbon dioxide, even though carbon to oxygen is a double bond, it's still just one group over here and one group over there. So 2 electron groups, they are bonding. Great. When we start looking at these illustrations, this is in your textbook where we have what we call a wedge and dash format. You do not need to know how to draw these. We will practice these in organic chemistry. I look forward to that day, and today is not that day. Now, for a molecule, once we've seen our structure, once we've done the Lewis, once we've done the actual VSEPR theory 3-dimensional shape, we can start to think about the polarity of the molecule, taking what Linus Pauling taught us and relating it now to a molecule itself. Here's the take-home message. If you have a polar bond, That's the first step. You need to identify, do I have at least one polar bond? And then, do I have an unsymmetrical shape? That will give you a polar molecule. Now, symmetry negates all of the idea of bond polarity, because if you're a perfectly symmetrical shape, you have vector addition and those vectors cancel. If you are unsymmetrical, so say you have different types of bonds, doubles, triples, singles, or you have one to oxygen and one to fluorine and one to hydrogen, differences make vector addition result in a polarity of the molecule itself. Non-bonding pairs, lone pairs, do not affect molecular polarity in terms of they are not polar themselves. However, they create that unsymmetrical shape. So if you have lone pairs and you have a polar bond somewhere in that molecule, you must have a polar molecule. A typical example is HCl. These binary molecules between just two atoms are a good representation of asymmetry. Hydrogen and chlorine. Chlorine is the delta minus, hydrogen is the delta plus. We have a polar molecule. Another example of a little bit bigger molecule that had a polar bond but is symmetrical is carbon dioxide. Yes, in terms of polarity, oxygen is delta minus, carbon is delta plus, and this guy is delta minus. But because of this perfect 180 degrees linear structure, our vectors for our polar bonds cancel each other out. So the overall net result, a non-polar molecule. There's symmetry at work. Now, water. H2O, if we were to do the Lewis structure, we'd start to see that there are 4 electron groups. There are 2 bonding and 2 lone pairs or non-bonding. And so that would be the tetrahedral geometry, but what we call bent. The lone pairs, if we want to imagine, they're up here. They take up shape. So imagine them taking up space right there. But what that creates is a vector addition problem, where our 2 vectors here are both pointing up towards the oxygen. The overall sum for the polarity of the molecule is that middle portion. What does that mean for us? This area down here is the delta plus. The area up at the oxygen lone pairs is the delta minus. So we can start to see polarity in the molecule based off of its 3-dimensional shape. If you need any help with vector addition, there is a good section in your textbook that talks about vector addition, when vectors are going the same way or opposite ways, if they're equal in magnitude or not. Take a look at that. If you haven't had calculus, it's taking an average of some vectors. And so if you need help with that, let me know. We can practice in class more. And again, vector addition going in 2 different directions, where you sum them up in the middle, 2 or more dimensions. That would be a good section to review if you haven't done any vector addition in calculus yet. Molecular polarity affects water solubility. This is something that we're going to see in general chemistry 2nd semester. Water is polar, therefore other polar molecules are going to be able to react with water, and ionic compounds are great to react here because of this charged nature of the molecule. And so that's where I'll leave you today. When we look at molecular polarity, it's really building up from the idea of Linus Pauling all the way back in determining, do I have a polar bond itself, through Lewis structures, through VSEPR theory, ending with what does my structure look like in 3-dimensional space, and how does my structure overall affect the polarity of the molecule. Thank you very much for joining me.